So the second talk will be given by Nachum Dershowitz from Tel Aviv University. He was formerly a faculty member at the University of Illinois at Urbana-Champaign. His research interests include theory of rewriting, termination proof, models of computation, natural language processing, and recently computational analysis of historical texts. Nachum?
Okay. So I want to thank the organizers for what until now has been a wonderful day. Yes. And not only is this theory day, it's still Turing's 100th year. And I want to second Chagit's invitation this morning to visit the capture exhibit in the Museum of Science in Jerusalem. It's a wonderful exhibit. They took ideas that some academics brought them 2 years ago and made it into something in which they're trying to explain the science as opposed to the engineering part of computer science. And I want to talk to you about the Church-Turing Thesis. And I'm motivated mainly by about 15 years ago, I started teaching computability at Tel Aviv University. And there were some vague things that we were teaching our students that distressed me. Okay, and this is joint work with various people, including Jenny, who's here. So I want to talk about various theses, about Church's thesis and Turing's thesis, which is the main thing, and a relativized version of them, and an extension of the thesis regarding complexity. And I won't talk about parallel thesis, but if I have time, I'll say a few words about a physical version of this thesis. But my goal is just to give definitions, taking this motto seriously that one definition is worth 3 theorems. He's a psychologist who tried to understand mathematicians. And I'll try to give you 3 definitions. What's an algorithm? What makes an algorithm effective? And how do you define complexity of an algorithm in general? And in general, I mean that it's language independent, data structure independent, that it should work regardless. The notions should apply to any programming language and to any kind of data. So let me begin with what's an algorithm. Well, Knuth pointed out way back that algorithms existed long before programming languages did, just as the concept of the number 2 existed before logicians defined them in terms of set theory. So we're looking for this prehistoric notion of algorithm. So back in the Garden of Eden, I'm trying to think what is the earliest algorithm I can imagine. So it's actually division. So I imagine Eve comes back with a basket of fruit and wants to divide it evenly between herself and her spouse. And this is her algorithm. She has a pile. She has a pile in the middle, and all she needs to remember is whose turn it is to get an apple. If it's her turn, she puts one in her pile. Now it's his turn. If it's his turn, one in his pile. It's my turn. Nothing left. I'm done. So these are the basic operations. Add 1, subtract 1, test for 0. In a nutshell, what I'm trying to claim is that the definition of an algorithmic process is a discrete algorithmic process is one in which you can describe the evolution of the process with some kind of finite description. And this is what we'd like to formalize this notion. So one of the earliest algorithms is here. This is Euclid's, the oldest manuscript of Euclid. Someone mentioned I'm interested in historical manuscripts. So Euclid describes actually 2 versions of the greatest common divisor algorithm, one for natural numbers and one for real numbers. And unlike the way we teach it, Euclid used repeated subtraction, not division and remainder. And here's the algorithm. This is the Greek. And so there's a finite description of 1 paragraph of text. This is what it says. When 2 unequal numbers are set out and the less is continually subtracted from the greater, if yet the number which is left never measures, in other words, not a multiple of the one before it, until a unit is left, then they're relatively prime. And okay, so we have that old algorithm. And this old algorithm doesn't work for Euclid. It worked with real numbers, at least one version of it. And Euclid's computer was a compass and a straight edge, not a Turing machine. So, but it's still a notion of an algorithm that we'd like to capture. Here's another algorithm you can't see very well. This is the 4th algorithm in the communications of the ACM's long-running column of algorithms from 1960. And this is simply a bisection search. You have this function that's positive and negative, and you continually bisect until you get root within some, you find the zero within some error bound. And as Saul Gorn, the author of that algorithm, said, this procedure, even though it's slow, it's wonderful because it works for any continuous function. And so it's an old workhorse that you can use whenever you want. So this is an example of an algorithm, but it's an algorithm that works on real numbers in some abstract environment. So what an algorithm is some kind of state transition system. So you have states, you have transitions, but the transitions are governed by some text, some finite text, what we call a program. So again, as Knut said, we want to think of a computational method as a set of states with a relation or a function, and then we can divorce the notion of algorithm from the particular representation as a program. So you have states, you have initial states, you have terminal states. At the end of a computation that terminates, and so you may have state last week, the state this week, and the transition function. Now, the transition function should be something mechanical. This is the idea of an algorithm, that you know how to get from one state to the next state without insight, without guessing, without more than that. In particular, I'm not talking about anything that involves random numbers, because random, even though you can implement them, like here, you'd be living in a state of sin. And I'm not talking about a continuous process, though I hope to get to it at the end of the talk. So not like making a souffle that if you open the oven at the wrong stage, pas souffle. So we're talking about a discrete process where the transitions are describable and are not dependent on input. We also don't mean something like these machines that run faster and faster, so in a finite number of times they can do infinitely many steps. No, or like Putnam's limit machines where you look and see what you get after infinitely many steps, and that's your output. No. We're talking about classical algorithms, and the state has to have all the information you need to determine the next state, other than the program itself, so that the state includes the operation. I mean, a state, you have all the information, including how to perform your basic operations. So you couldn't have, in an algorithmic deterministic process, something like green state, green state, green state, blue state, where these three states are identical. So why here do you go to green and here to blue if it's deterministic? So if you want something like that, you'd have to count. Okay, so the states include all the information you need for determining the next state. Yes?
So computation is any process. For example, you have a bomb, the state that it's not exploded, the second state that it's exploded, and this is a computation?
No, I'm working my way towards a definition of what makes an algorithm. This is just a description. Okay. This is step one out of 4. Okay, so and a point that Turing makes very clearly is that the state includes all the information, so that if you go out for a coffee break, as I hope to get to soon, and you come back, you can take off. You can continue from where you left off. All the information is in the state. This is what we call instantaneous description of a Turing machine. But in general, all the information is there. This was the great discovery, of where you so the point of having discovered pastel crayons is that you can take a break and the oil won't dry. Okay, so the state has everything other than the algorithm, and we want something generic here, that not just numbers, strings, but it should work for any and all data structures. So Post, already in this unpublished work in the 20s, pointed out that you can describe a state as a relational structure, and that any state of any computation can be viewed as this, what he calls a symbol complex, which is completely determined by the relations between the parts, though he was speaking about a finite representation. So that's what states are. So let's say states are first-order logical structures that have all the information we need to describe what's relevant. So it includes not just the values of variables, but also the meanings of the functions, or how does a compass work, how does the ruler work, and so on, if you're doing geometric algorithms. So in the example of the bisection search, we have the constants A, B, but you also have these operations, addition, subtraction, division. All this is part of the state, and some of it changes during a computation. In other words, the algorithm might change the meaning of X, or might change the meaning of an array F. And so the transitions change the interpretation that the structure gives to its symbols. Okay, so to summarize, so far states are logical structures. All the states of a particular algorithm share the same vocabulary, and the transition will preserve the domain of the states. So you can have state where this is a state, and this is the next state. Sorry, and if you're doing your measurements here in Celsius, then the next state is also doing measurements in Celsius. That's only preserving the domain. Okay, furthermore, we want the states to be abstract. In other words, you can describe an algorithm on any level. You don't have to say how you represent numbers. You just have to say how to add, regardless of the representation. So the behavior doesn't depend on whether plus 5 volts is positive or negative in a particular implementation. So that the states are closed under isomorphism. So whether you measure things in Fahrenheit or Celsius doesn't matter as long as your operations are defined accordingly. So you want the transitions to commute with the isomorphisms. So if the state changes from cloudy to sunny, temperature goes in centigrade, the same program should work on a different scale. States are abstract. It doesn't matter if you represent numbers as in binary or numbers as platonic numbers. If your operations are working on numbers, it's the same algorithm. And when I said first order structures, that just means to exclude syntax that's not first order, like the minimum of infinitely many values. So Kleene said an algorithm should be fully and finitely described before any particular question is applied or selected, and without ingenuity or mathematical invention. So how do you capture this formally? The notion that it can be described finitely in a language-independent manner. So furthermore, each step should only depend on a finite amount of operations, so that you work in discrete steps where each step looks at only a bounded part of the state in order to determine what the next step is. So Yuri Gurevich proposed this abstract way of saying that there's a finite textual description by saying transitions are determined by a fixed finite set of ground terms over in the vocabulary of the structures of the algorithm. And that when two states agree on the value of all those terms, basically agreeing on the values of everything mentioned in the program, however the program may be written, then the algorithm should be doing the same thing to the two states, make the same changes to the two states. So never mind the technical aspect, but if these are the terms mentioned by the program, x and fx, so you have a state, the state may give a value to x, it may give a value to f of 3, f of 1, and so on. What I mean, these finite set of critical terms, or those things mentioned in the program, in the finite description or the transition, means that if you have two states that agree on the value of x and f of x, so these two states agree on x being 3 and f of 3 being 5, then the changes they make, changing x to 1 and f of 3 to 0, are the same in the two. But anything that doesn't change, that's not mentioned here, doesn't change. So f1 is 7 here, it stays 7. F1 is 2 here, stays 2 here. It would not be algorithmic if f of 1, which isn't mentioned in the program, magically changed from 1 to 4. So the point then is, if you have two states that agree on interpret all the critical terms in the same way, then the changes made here are the same as the changes made here, and everything else stays the same. So there have been three postulates of what an algorithm is. An algorithm is a discrete state transition system that we can use logical structures to capture states, and that transitions can be described finitely and also commute with isomorphism. And then Gurevich proved that any process that satisfies those postulates can be emulated step for step by something he called an abstract state machine. An abstract state machine is a very simple, generic programming language that just has three instructions. An assignment, general kind of assignment, where these are terms. A conditional, if some Boolean term is true, then do some program P or else Q, and then do everything in parallel. Then an outside loop, do all these conditional assignments in parallel. And he proved that that any algorithm satisfying the postulates I just showed you can be emulated by a program in this programming language. And the point is that because it's isomorphism closed and you have this finite set of critical terms, there's a way to describe the transition in a text in this text, which he calls the abstract state machine. So Gurevich's result needed to be generalized slightly for the things I'm getting to handle also partial operations. So rather than saying that a partial function returns some undefined value, I need partial functions to really be partial, so that if an algorithm tries to access a partial function where it's undefined, then it's going to hang. It's not going to return undefined. It's not going to return anything. It's going to get into this black hole here. And so, for example, if you want to do matrix inversion and you have a division operation that's partial, and you don't want to divide by 0, then you want an algorithm that first computes the adjoint, which so you don't do any division, and only if the determinant is 0 do you define, and also only if the inverse is undefined should you get an undefined operation, but never unnecessarily do access an undefined operation. So, for example, if this is a program, what I'm trying to say is that I want to say that any algorithm that is also algorithmic in the sense of which values it looks at can be exactly emulated by a program in this language of parallel conditional assignments. And so that here, these 3 assignments, they look at the value of A. Only if A is true do I need to look at B. And only if A and B and C are all true do I need to look at X. So only if A is true do we access B. And B may be undefined. If A is false, I don't care. And therefore, we can say that every algorithm satisfying those postulates you saw, plus some extra statement about which locations in the state are looked at, should also be algorithmically defined, can be emulated step by step, state for state, by this kind of abstract state machine that does exactly the same thing. It looks at the same locations, extracts the same values, and makes the same changes. So now we're ready to deal with the Church-Turing Thesis, which is a question of which algorithmic processes are effective. So the question is, what can we do mechanically, and what can we not do? So there are various algorithms. So Euclid's algorithm, the antineresis algorithm, for GCD was a compass and a straight edge algorithm, as was the algorithm for constructing a tangent. Gaussian elimination, the same algorithm works for real numbers or complex numbers or some other, and can be described in a non-effective manner. Or the bisection search we saw was a non-effective algorithm. And the reason we want effective algorithms is to make good on Leibniz's dream of doing logic by calculation. And as Lovelace Ada recognized, the fact that a computer, or Babbage's analytical engine, works with numbers doesn't mean it's a universal machine that can compute any function of any complexity. And we want to apply that to be able to solve, to do reasoning. That was the point. To find an effective algorithm, for example, to determine whether a formula is valid or satisfiable, was Hilbert's Einschränkungsproblem, which was considered, of course, the most important open question then. And what we're looking for is an algorithm, something that you can do step by step and perform effectively. So they were interested, is there an effective algorithm for logic, for arithmetic, for geometry, and so on? And again, what makes an algorithm effective is that you have this sequence of steps, and each step takes a finite amount of time, unambiguous method to perform algorithms step by step. which brings us to Poincaré, who imagined this as like the legendary factory in Chicago, where live pigs go in one end and sausages come out of the other end, axioms in one end, and out come the theorems. That was the goal. So Church said, let's look at recursive functions, which are defined by some set of equations on zero and successor, or the way we more normally look at recursive functions, and claim that recursive functions capture effective computability on the natural numbers, that these are exactly the set of functions that can be calculated effectively. So he said, let's define effective function to be a recursive function. Well, not everyone is happy with this as a definition. Kleene, here's the exact formulation: a partial function is effectively calculable if it's partially recursive, what they call then potentially partially recursive. So what I'd like to do is to make this, to prove this thesis. And even though we usually say that it's not the kind of thing you can prove, let's formalize it and prove it. What does it mean for an algorithm to be effective? We already know what an algorithm is, so now we only need to know what makes an algorithm effective. Church's thesis was about recursive functions. Turing came up with an alternate notion of a computing machine. That's a human being operating paper, pencil, and rubber, following rules, gives you a Turing machine. I'd like to mention again that the museum in Jerusalem gives an example of several Turing machines, in particular two-dimensional Turing machines working on two-dimensional input-output, changing colors, and programs, some kind of flowchart program telling you whether to go up or down or left or right, and to look at the color of the square. That's what Turing invented. So two-dimensional Turing machines require less encoding than one-dimensional ones, so they work well. And Turing's contention was that these Turing machines capture exactly what humans can do mechanically, algorithmically, effectively. So once Turing proved that recursive functions and Turing machines compute the same numeric functions, then so Kleene could say Turing and Church's theses are equivalent, saying that a Turing machine does everything effective, or the recursive functions are everything that is effective is equivalent. But since Kleine's advisor was Church, he called it the Church-Turing Thesis. So that is the Church-Turing Thesis, that any effective computational model is no stronger than a Turing machine in some sense. Why is this interesting? Well, we saw why, because this allowed Church to prove, or Church as explained by Turing, to show that the Einstein's problem is in fact undecidable. In the sense that there is absolutely no effective way of solving it. And this Church recognized. As did Gödel only after Turing gave his very fundamental definition of what's computable based on what the atomic operations that a human can do when calculating, do we know what it really means to be effective. So why do people believe this Church-Turing thesis? Not for three reasons from the beginning. One is that all these models, Church and Turing, post machines, Markov algorithms, Kolmogorov algorithms, and so on, they all give us the same class of functions. That's not very convincing, because maybe we're missing something. For a number of years, people thought that you couldn't compute more than primitive recursive functions, and they were wrong. Maybe we're still wrong, and there's more to effective algorithms than the recursive functions. Second reason given is that no one's come up with anything that is both reasonable and super Turing. Well, only 50 years have passed, so maybe we'll still come up with something. But the only convincing argument, I think, is Turing's own analysis in the end of his paper, and where he explains why computation is symbolic and why should only have finitely many internal states, because otherwise you couldn't distinguish between states, why only finitely many symbols, because otherwise you couldn't distinguish between different symbols, and why you only look at a bounded number of squares and to decide your next step, and so on. This is relatively convincing. But still, it's not complete, and I'd like to complete it by considering not just string algorithms, but by generic algorithms. And so if you accept the premises of what makes an algorithm effective, then we can try and prove that, in fact, any effective algorithm is computable by a Turing machine. All right, so we already saw three postulates of what it means for a process to be algorithmic. Basically, that there's a finite description of state transition and states are arbitrary structures. And so as Gödel and Schoenfeld and others suggested, if we can axiomatize what it means for a function to be effectively computable, then perhaps, and if you all agree with me, I hope, that the axioms are reasonable, then we might be able to, and we can indeed prove Church's thesis from it. Okay. So, in a nutshell, I want to say that an algorithm, which you already know what an algorithm is effective provided the initial states also have a finite description. Not just transitions have a finite description, but also initial states. And of course, since transitions have a finite description, if initial states have finite transitions, then every subsequent state also has a finite description. So the initial state, not only does it have a data value of the input, it also has operations, the basic operations that the algorithm is using. And so if it's effective, it means that certainly you could have addition, subtraction, that we know how to do, but you don't want things we don't know how to do in the initial state, like the halting function. Because addition we can describe finitely, and the halting function we don't know how, effectively finitely. But of course, if the initial state had something non-computable like the halting function, then obviously we'd be able to compute more than Turing machines. So we want to exclude magic or hotlines to heaven or something, that's the witch of Endor, from your initial states. But to get to that, let's first start from the case where we do have an oracle. We have Turing's oracle here, and so that the general notion of algorithm, the initial state could have magical information such as an oracle. So that's what Turing said. So let's first prove, or not prove, but claim to prove, a relativized version of the Church-Turing Thesis, in which we're not dealing just with natural numbers, but with arbitrary domains. So what we're interested in is the notion of effective for an arbitrary domain, not necessarily numbers or strings, using other data structures. And what Ada said is that you can represent anything by a number, and this is true. I mean, she's criticizing people who thought that just because the analytical engine works with numbers means that it couldn't do something algebraic or logic. That's wrong. Because we know how to represent things. We can arrange and combine numerical quantities as if they were general symbols. Okay. So imagine even an algorithm that the operations are only graph operations. You have a graph function predicate P, a graph function G, a constant graph C. You can still define a numeric function as, for example, the minimal I, such that you get for input n that P is true when you compose G I more times. So we need to be able to, even if we're interested in numeric functions, to be able to work with arbitrary data structures. So Church worked with numbers, and we have the notion of recursive functions. Turing worked with strings, we have Turing machines. But this abstract state machine that I spoke about can work with arbitrary domains. So imagine that the domain has a fixed finite set of constructors. These are free constructors, giving us a Hilbert universe of the domain. So every value of the domain has a unique name in terms of the constructors. Forget that. So, okay, Turing proved that the recursive functions in Turing machines are equivalent, or partial recursive functions and the partially computable string give you the same numeric functions. But more generally, we can have recursion equations in terms of other basic operations, not necessarily zero and successor. Or we can have oracles in the Turing machines. These correspond to the functions you have in the initial states of an abstract state machine, which can also be arbitrary infinite operations. And to make this, to speak of effective, there are three ways of doing this. In the church context, we can talk about tracking the functions on other domains. And let me explain. And it'll turn out that these are all equivalent definitions, so we've really captured the notion of what it means to be effective with respect to oracles, or more generally effective with respect to the basic operations. So what does it mean, a computable algebra? This is a notion that Michael Rabin had, for example, to generalize computability for any algebra, where you're saying that you can simulate the operations of the algebra. If you want it to be effective, they have to be simulated by partial recursive functions. What it means by simulated is that you assign numbers to the domain objects, and that the operations you have on the domain objects, like this operation, correspond to something that's recursive in the numbers. And if you want recursive in other operations, then it has to be that you want to track your operations in other domains by something that you agree is effective. If we're working with Turing machines, Wolfgang Reisig had this idea that what you want, that an Turing algorithm is effective if you can decide the equality of the terms that represent data values, in the sense of a Turing machine decidability or partial decidability. But the most, I think, natural definition, is that to use an abstract state machine where you have constructors. You have these free constructors, or anything you can build from free constructors in your initial states. This is what you have in order to manipulate domain values. So you have names for everything, and you have operations that can be described in terms of those constructor operations. And anything you want beyond the constructors themselves, which have no relations, there are no equalities between constructor terms, you have to program yourself or bootstrap it. So the natural numbers, you have 0 and success. So binary trees, you have a constructor for binary trees, and so on. So whatever your domain is, you have these constructors, and you can prove that these three notions of effectiveness. One is that that you can track the operations on your domain by recursive functions, or that you can decide equality of arbitrary terms in the vocabulary of the program, or partially decide them, or that you can define all the basic operations in terms of constructors are equivalent. They're equivalent even in the sense that if you take everything you can program, all the programs, they give you exactly the same set of functions. These are the effective functions. And in other words, Turing machines, if you talk only about without oracles, Turing machines simulate all effective models, everything that satisfies the three postulates of what an algorithm is, plus that everything in the initial state is programmable from constructors. Any algorithm satisfying that can be simulated by a Turing machine. And Turing machines, no matter how you represent, no matter what injection you use from the domain into strings, a Turing machine can't do more. Okay. If you don't believe the Church-Turing Thesis, and there are various people who don't believe the Church-Turing Thesis here, then, or some, never mind, one of these perhaps doesn't satisfy the Church-Turing Thesis, then it means that it must violate one of the four principles you've heard. Either it's not a discrete state transition system, so you have something transfinite or continuous in your evolution of states, or perhaps you have some non-first order operation. You have some infinitary operation where you look at, running the program any number of steps all at once. So you have an infinite program, not a finite. You don't have a finite description for your program, or you already have something uncomputable in the initial states. One of those must be true if you claim to have anything that can hypercompute. Now that we know what it means to be an algorithm, what it means to be effective algorithm, we can ask a general question: what is the complexity of an arbitrary effective algorithm of an arbitrary domain in an arbitrary language? And this leads us to what's called the extended Church-Turing Thesis, which claims that not only do Turing machines simulate every effective algorithm, but Turing machines can simulate them efficiently, in other words, polynomially. So-called extended Church-Turing Thesis, that any function which we might regard as being efficiently computable can also be computed by a Turing machine. So, well, we have to decide what do we mean here. How are we going? We have some. We're going to compute it. How do we count steps? How do we measure the size of the input? We need to decide. Now, so here in this survey of models of computation, Van M. Du Bois writes that register machines, random access machines, and the like have become the standard model for complexity concerns, and that if we can show that all reasonable models are polynomially simulatable by each other, then we can be happy with this choice of register-based machines. And he said he firmly believed that complexity theory is based on the assumption, which he calls invariance thesis, that there's some standard class of machine models, in particular the RAM model, that polynomially simulates every other model. So we can prove that from the definitions we have already. So that we need not just abstract state machines that use constructors, but we said that the initial state of a effective algorithm have operations that can be programmed in terms of the constructors, but we want to measure are the steps, the constructor steps, not these large operations like multiplication or something that we wouldn't want to count as a single step. So you have construct operations, destructors, and equality. That's what you're given. Those are your unit operations, and that's all. And so you measure the size of the input by how many construct operations you need to build it, and we count the number of steps in this basic algorithm, basic abstract state machine, in order to, relative to the size of the input. And so you can prove that any basic effective algorithm can be simulated by, in fact, by a RAM very efficiently. So you take we can take some version of Schoenhager's pointer machines that Dexter, Doyle, and Gurevich proved can simulate some class of algorithms that include our basic algorithms, and any of these Schoenhager machines can be simulated each step with a constant number of steps using a multidimensional random access machine. So you have these arrays here, 2 arrays, multidimensional arrays, and use them to record the pointers, and all's well. So that, in fact, we can prove that any effective algorithm that computes in T of n steps can be simulated by a RAM in some constant times the number of steps. Okay, what about something magical like a quantum computer? That leads us to what's been, could be called the physical Church-Turing Thesis, though sometimes people omit the word physical and get us confused what they mean. So the physical Church-Turing Thesis says not that there's no way for human to compute or no mechanical way to compute, but that we cannot even build any physical device that can do better than a Turing machine. So this is a claim about physics. Gandhi distinguished explicitly between Turing's thesis and this machine thesis, thesis M, which says that anything that can be calculated by a machine is also, by any physical machine, is Turing machine computable. So just a few words about that. So go back to Galileo, who was conveniently brought up this morning. So Galileo pointed out that in order to understand physics, you need to learn the language of the universe, which is, of course, the language of mathematics. So that we can, this is miraculous, that we can describe, that we believe, scientists believe that they can describe the universe by means of equations. So Gandhi formulated what are these sort of these principles of physics, that if you believe these principles of physics, then, in fact, this physical Church-Turing Thesis is true. You need to believe that the laws of physics are the same every time and every place, that they don't change from place to place, that in any finite space-time you only have a bounded amount of information, that you can only, in a fixed length of time, you can only get information from some finite bounded radius from where you are, and presumably initially all but finally many units of space-time are identical, so that only a few places are different from all the rest of the universe. Okay, so physicists don't believe this, that there's bounded density information in states. They believe that in bounded space-time you can have infinitely many different states. Some physicists might believe that you can only measure finitely differences between finitely many states. Okay, so that leads if you really want to think about physics, we need to formalize something that we started trying to do, computation in continuous time. And okay, so that's continuous time. Okay, so normally what it means, let me skip to something. So continuous time is very different. Okay, you can have in one step uncountably many changes. You know, like this is Nixon's tape recorder. You know, you push the erase button, you've changed the function for uncountably many places. Different kind of analog computers, never mind. So in this world, you have two kinds of things going on normally. You have what's called a flow, which is some for some stretch of time, some equations are kept continuously, but the equations themselves, the same equations stay true over a period of time, and so that the dynamics are fixed for some stretch of time. And then at some point, you may have what's called a jump. The dynamics change. And you want to model this by something similar to this abstract state machine in a continuous context. Okay, so never mind. Thank you very much. And be happy to answer questions. If there are no questions, I assume that you've been convinced by the proof of the Church-Turing Thesis and the extended Church-Turing Thesis. Thanks.
You're trying to prove in the physical Church-Turing Thesis that anything you can build in the physical world is no better than the Turing machine. But I think that
no, I wasn't trying to prove it. I was just trying to formalize it. If you believe it.
But you cannot even build a Turing machine, the physical world, because, for example, it needs an infinite tape.
Yeah. Well, we're talking about idealizations in any case. So the question is, in an ideal world, how do you define what means to be ideal in the physical world? You can then you ask the same: can you build a device that computes more than a Turing machine, an ideal Turing machine could, using an ideal physical model of the universe? And these are all. Yes, I agree. Everything is just a finite automaton. It makes errors. So. Yeah, that's why this is a theory day.